Hi boys and girls, this is lecture 3.6 in Unit 3. The topic, related rates. Today's lecture will comprise part 1 of this discussion. We have finished learning methods for differentiating, and in today's lecture we'll discuss an application of the derivative. Another important use of the chain rule is to find the rate of change of two or more related variables that are changing with respect to time. Anything in motion represents a quantity that is changing with respect to time. This could be a velocity, a distance, a volume, some sort of growth rate, anything really. The list is endless because so many things are in motion. Let's take a look at the classic ladder problem. We have a 20-foot ladder leaning up against a wall, and you can see that it forms a right triangle with the wall and with the ground. At this moment in time, before the ladder starts to move, the lengths of the triangle are static. Of course, the length of the ladder is not going to change, so the hypotenuse will remain constant, but this distance from the base of the ground to the height of the ladder is a defined distance at this point. The distance from the base of the wall to the base of the ladder is a defined distance at this point, and all three of these lengths are related to each other by this equation, the Pythagorean theorem. Now, the ladder doesn't remain still. It begins to move down the wall, and as it does, the y distance begins to decrease, the x distance begins to increase. As it does, the triangle begins to reconfigure itself based on the movement of the ladder. Let's look at a couple of other configurations of this triangle. This blue line is the same length as the ladder, but you can see that the triangle is very different. The y distance is shorter, the x distance is longer, yet all three lengths are still related to each other by this formula. Here is another configuration of the triangle. Again, the pink line is the same length as the ladder, but a very different triangle, yet all three lengths are still related to each other by this Pythagorean theorem. Not only are we interested in the changing lengths of the triangle as the ladder moves down the wall, we're interested in the rate at which these lengths are changing. How fast is the ladder moving down the wall? And how fast is the base of the ladder moving away from the wall? These are rates with respect to time. The rate at which y is changing with respect to time would be represented by this differential, dy dt. Notice it's not taking the derivative of y with respect to x anymore, instead with respect to time. The rate at which x is changing with respect to time would be represented by this differential, dx dt. Again, the derivative taken with respect to time. Not only are we interested in these rates, we have other questions as well. Will the rate at which y is changing be the same as the rate at which x is changing? Furthermore, will these rates be constant or will they vary? Will the ladder move down the wall at a constant rate, or will speed begin to increase as it moves down the wall, or decrease? All of these are very interesting questions that we would want to have answered. The derivative of a geometric formula such as this one, using differentials such as these, will give us all of the information we need about the classic ladder problem. Let's find the rate of a falling ladder. We have our 20-foot ladder leaning against the wall of the house. It hasn't begun moving yet, and at the moment just before it moves, it turns out that the base of the ladder is 12 feet away from the base of the wall. Furthermore, we see that the base of the ladder is being pulled away at a rate of 2 feet per second. That's the rate at which this x distance is changing with respect to time. So dx dt is 2 feet per second. How fast is the top of the ladder moving down the wall when its base is 12 feet away? So the question we're being asked is, what is the rate at which y is changing? The variable we're going to want to solve for is dy dt. That's what we're looking for, that rate. Well, first of all, we need a formula or an equation that relates all of these quantities. As we have seen before, for this problem, that's going to be the Pythagorean theorem. X squared plus y squared equals 20 squared. Anytime you are setting up a related rate problem, you'll have to use some formula which relates the quantities involved. That's going to be some sort of known geometric formula, like the Pythagorean theorem, or an area formula, or a volume formula. Once you have set the formula in place, the one that relates all of the quantities involved in the specific problem that you're doing, then you can use that as the foundation for taking a derivative and discovering the quantities that you will need. Furthermore, when you set up that equation, you have to pay attention to the quantities that will vary and the ones that will remain constant. For example, in our problem with this right triangle, the hypotenuse is not going to vary. So when you set up your equation, you don't use a variable there, you use the numeric value of that quantity. However, y is going to change and x is going to change as the ladder starts moving down the wall. So you have to use variables in the formula for those two quantities. Now, using implicit differentiation kind of techniques, let's take this derivative. Every variable that varies is going to be assigned a differential with respect to time. And so we will say the derivative of this first term is going to be 2x and then dx dt. The differential regarding x changing with respect to time plus 2y dy dt. This differential represents the rate at which y is changing with respect to time, and of course the derivative of 20 squared, a constant, is 0. Now this function will allow you to find all of the information that you need. You have what is x at a specific moment in time, what is y at a specific moment in time, what is this rate at a specific moment in time, and what is this rate at a specific moment in time. Since in this equation there are 4 variables, you will need 3 known quantities in order to solve for the 4th variable. This is what we're solving for here, dy dt. So we need y, x, and dx dt. Let's go back to the problem and see what we were given. We do have dx dt, we do have x, but we don't have y. Fortunately, we can use the Pythagorean theorem to solve for y. In this problem, we have x, which is 12 squared, 12. We square that, plus y squared equals 20 squared. That's 144 plus y squared equals 400. That means y squared equals 256, which means y is 16. So in this configuration of the triangle, when the hypotenuse is 20 and the x distance is 12, the y distance is 16. I'll put it here so we can see it. All right, now we have the 3 variables that we need in order to solve for the 4th one. So let's do that down here. 2 times x, which is 12, times dx dt, which is 2, plus 2 times y, which is 16, times dy dt, the variable that we're solving for, equals 0. This becomes 48 plus 32 dy dt equals 0. When we subtract 48, we end up with 32 dy dt equals negative 48. Dividing by 32 gives us dy dt is equal to negative 48 over 32, which reduces to negative 3/2 feet per second. So the rate at which the ladder is sliding down the wall at this moment is negative 3/2 feet per second. Notice it's a negative rate because the y quantity is decreasing. The reason why the x rate was positive is because the x value is increasing as the ladder slides away from the wall. Now realize that these rates only apply when the x distance is 12 and the y distance is 16. As the ladder begins to move down the wall and the triangle begins to reconfigure itself, then different rates apply. Yet we have a function here which will allow us to solve for any of the four variables given the other three quantities. So this function will provide all of the information that we need about the falling ladder. Here are some general guidelines for solving related rates problems. Identify all given quantities and quantities to be determined. Make a sketch and label the quantities. It's always a good idea to make a sketch. It helps you to visualize the relationships between the variables and the quantities given. Write an equation involving the variables whose rates of change either are given or are to be determined. Remember to also pay attention to which quantities are going to remain constant and which ones vary, and set up your equation accordingly. Using the chain rule, implicitly differentiate both sides of the equation with respect to time t. After completing step 3, substitute into the resulting equation all known values for the variables and their rates of change. Then solve for the required rate of change. Let's look at another related rates scenario. A pebble is dropped into a calm pool, causing ripples in the form of concentric circles, which is what we see depicted here. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? Let's first of all identify the quantities that were given and the one that we're trying to find. We're being asked for the rate at which the total area A of the water is changing with respect to time, and that's going to be dA dt. We are given the rate at which the radius is changing, dr dt. That's 1 foot per second. And we're also given the radius at this moment in time, which is 4. Remember, the radius doesn't stop here. It's going to continue to increase as time progresses. And different rates would apply. But essentially what we've done here is we've taken a photograph of this situation at this moment in time, and we're going to set up a mathematical model in order to discover the quantity that we're looking for. Now we're going to need a formula that relates the area of a circle to the radius of a circle. Remember, it's a known geometric formula. You don't have to create one. It's going to be an area, a volume formula, the Pythagorean theorem, and of course in this situation we don't have to look far to find the formula that connects the radius of a circle to the area of a circle. This is the formula that we want, the area of a circle formula, connecting the area to the radius. We're going to differentiate this formula implicitly, and every quantity that is changing will be assigned a rate differential. As it happens, both area and radius are changing in this situation. Remember that pi is constant, so it's just going to function as a coefficient here. The derivative of a then will be dA dt, 1 dA dt, equals pi times the derivative of r squared, which will be 2r dr dt. To rewrite this, I'm going to have this function, 2 pi r dr dt. This function will give me any of the quantities that I want given the other two. Of course, I'm being asked to find this one, the rate at which the area is changing with respect to time, and so I will need a radius and a rate at which the radius is changing. Fortunately, that's exactly the information I was given. So let's plug in these values and solve for the rate that we're looking for. dA dt then will be 2 pi times 4, the radius at this moment in time, times 1, the rate at which the radius is changing. This is 8 pi, and since this is the rate at which an area is changing, our units will be feet squared per second. You have to assign correct units to your rates or to whatever quantity you're solving for in a related rates problem. In our last example, we're going to explore the quantities and rates involved in an inflating balloon. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Remember that the rate of change of the radius and the radius are two different variables. So let's see what's going on here. Air is going into a spherical balloon. As it does, the radius of the balloon is changing, the volume of the balloon is also changing. What do we have and what are we being asked to find? We're being asked to find the rate of change of the radius, so that's dr dt. That's our unknown. What were we given? We were given the rate at which the volume is changing. That is 4.5 cubic feet per minute. We were also given the radius at a specific moment in time, 2 feet. Remember, the radius won't stop here. As air continues to go into the balloon, the radius increases, the volume increases. But in effect, we've taken a snapshot at this moment. We're going to create the mathematical model, which will allow us to answer the question given this information. Of course, now that we have the quantity that we're looking for and the quantities that we were given, we need a formula, an equation that connects the radius of a sphere to the volume of a sphere. We look through our catalog of known geometric formulas and we find, to our happy relief, the volume of a sphere formula. Notice it connects volume to the radius of a sphere. And that's all we need, something that relates the variables to each other. We can differentiate this formula and find the quantity that we're looking for. Now, in this formula, there are two variables, volume and radius, and they're both changing with respect to time. 4/3 and pi are constants, and so they simply function as coefficients here. Let's take this derivative. The derivative of v is 1 dv dt, and then we'll have 4/3 pi times the derivative of r cubed, which is 3r squared dr dt. To simplify this a little bit, we'll have 3 times 4/3 gives us 4 pi r squared dr dt. Now this function will give us any information we need about the rates involved in the inflating balloon and the radius at any moment in time. But we're interested in the time at which the radius was 2 and dv dt was 4.5 cubic feet per minute. So let's plug in those quantities and solve for dr dt. We're going to have 4.5 equals 4 pi 2 squared dr dt. 4.5 equals 16 pi dr dt. And dividing both sides by 16 pi gives us 0.09 feet per minute equals dr dt. That's the rate at which the radius is changing with respect to time when the radius is 2. Interestingly enough, as the radius increases, this rate will change, even though the volume is changing at a constant rate. Remember, this is being pumped in, not at a variable rate, at a constant rate. It's so interesting that even though the volume is changing at a constant rate, the radius is changing at a variable rate. So many fascinating things to discover about inflating balloons. And that's it for today's lecture. It's always good to have one of these, isn't it? God bless you, boys and girls.